I think if we keep I'll definitely be yeah, I have to. There were so many people. That one guy, after the first touchdown, he was
Okay, so let's see. Welcome back. Hopefully you guys aren't too distracted after the week's game. Perhaps wet day. I came from Michigan, so I'm picking back up in the example that we left off on last time, dealing with fluid drag, right? And so we talked about how the flow around objects is going to depend on the shape of the object with blunt bodies, things like spheres, cylinders, blocks, bricks, whatever. They tend to develop what's called a separated flow, okay, a wake behind them where the flow detaches and leaves behind this vertical mess that can increase the drag. And we said that it actually turns out that turbulent flow around one of these objects tends to make the flow better able to stick to the object. So it reduces the amount of separation. And a prime example is a golf ball. And so this little example here, we said, all right, if a good healthy drive with a golf ball has a diameter, has a speed of around 60 meters per second, okay, then what would be the drag on that golf ball, relative to if it were made perfectly smooth, right? The kind of the conventional wisdom would think that a perfectly smooth golf ball is going to have less drag, right? All those dimples probably increase the amount of drag on the surface. But if we actually run through the numbers here, we say that we want to know the Reynolds number, which is going to be, right, the speed times the diameter of the ball over the kinematic viscosity. So let's say 60 meters per second times 0.043 meters divided by 1.12 times 10 to the negative 6th meters squared per second. And I did not write down the solution beforehand, so I'm going to do this live. 60 times 0.043 divided by 0.2. And why am I getting such a bogus number? One moment. I'm getting way too big of a number, actually. Oh no, I'm not. My mistake. Sorry. I'm getting 2.3 million times 10 to the 6th. All right. So that's going to put us. No, that is too big. Am I off by a order of magnitude here? Well, all right. Forget it. Doing it live didn't work. I'll just give you the broad strokes here. What we're supposed to do, I'm wondering if one of the numbers I put up here is a little bit off. But what we're supposed to get, okay, is a Reynolds number that is right about here. So it should be about 2 times 10 to the 5th. And we see that right here, our smooth sphere has almost a maximum in the drag coefficient. Okay. Whereas our golf ball is a much smaller value. In fact, it goes from about 0.5 to about 0.25. And so our golf ball actually has half the drag coefficient, which at the same speed is going to mean half the drag. And we can see sort of why, again, through this little image that shows that the smooth sphere is going to have a laminar boundary layer. And because the laminar boundary layer doesn't mix energy as well, it isn't able to bring that high energy from outside of the boundary layer in. And so it runs out of energy and it detaches. Whereas the turbulent flow, because it's mixing flow around, tends to be able to stick to the surface better. And the flow detachment region is much smaller. The trade-off there is that turbulent boundary layers do produce more drag in the portions where they are attached, which means that the drag on a golf ball never gets as low as the drag on a smooth sphere, but it is smaller in a more useful range of Reynolds numbers that are the range where a person can actually drive the ball at about those speeds. So, but what we're here to talk about today is our very last topic of the class, which is fluid dynamic lift. And so our objectives describe how lift forces originate from flow around a body. Second, use lift coefficient to calculate lift force, similar to what we did with drag. And describe the action of airfoil sections, right, which are the shapes that we, most frequently see employed for things like wings and propeller blades, wind turbine blades, etc. They're shapes that were designed specifically to create lift with a minimum of drag. So I'm actually going to jump back over to the slides here for a moment. So a quick little recap, right? Lift and drag. At this point, we've said that flow around an object has 2 ways that it can interact with that object: through the pressure distribution shown on top, which can be positive, negative, right? It can either be pushing or pulling on the object, as well as by the tangential shear stress. And so we said we divide this surface into a bunch of little pieces with pressures and shear stresses acting on each little piece, then we were able to write the equations for the drag, which is aligned, parallel to the flow, and the lift, which is normal to the flow. And then finally we said, because these are difficult to actually know, because the pressure and the wall shear stress are generally not known everywhere, we instead tend to stick to either simplified models or experiments and use the drag coefficient and the lift coefficient instead, because those are dimensionless and already tabulated for us. So, focusing on lift, right? Some of the characteristics of lift here. The first thing is that if the flow around the body is symmetric, all right, the pressure distribution around that body is also going to be symmetric. We saw an example of this with that, like that triangular bar. That's a really poor triangle. That triangular bar where we said if there's flow occurring around this, right, we had a pressure distribution that was the same on the top as it was on the bottom, and so they canceled each other out, and there was no resultant force perpendicular to the flow. So the point is that lift requires some asymmetry in the flow. Introducing this a little bit early, but foils are objects that were designed to generate lift, and they're usually somehow optimized to do so with a minimum amount of drag. So this is an example of a foil, right? It looks like what would happen if you cut a fan blade or a propeller blade or an airplane wing in half and looked at the cross section. And the idea is that with a section like this, if it is oriented, a symmetric section like this, if it's oriented straight on into the flow, then the flow around it is going to be symmetric and no lift will be developed. If instead it was angled with respect to the flow, which is shown here by the flow coming in from this angle of attack, then you're going to develop some, you're going to have some asymmetry and you'll develop a resultant force. Swap back out of here. So lifting bodies, like these airfoil sections, the idea is, like I said, they're designed so that they produce lift when they are somehow oriented in a way that is not symmetric with respect to the flow. So we saw the example of a symmetric foil. Must be inclined with respect to the flow to develop lift, and so that means is our symmetric body has to be angled so that the flow around it will become itself asymmetric and develop a lift and a drag. Lift and a drag. What are called cambered lifting bodies are asymmetric on their own, meaning that they don't require this inclination in order to have some asymmetry. And what they'll look like is something like this. This is kind of, you can see this in nature, looking at the shape of like a bird's wing, where they tend to have some curvature to them. And so even if the nose and the tail are oriented horizontally, the flow around this is going to be asymmetric because of the two surfaces, the upper and lower surface themselves are not symmetric, and you'll develop a lift and a drag. The decision of whether to use a cambered versus symmetric lifting body depends a lot on the engineering application. The principal difference is whether you always want to be generating lift in one direction or if you want to be able to swap it back and forth. So if you want an airplane wing where generally you want the lift to be in the direction that is not driving you into the ground, they're going to be optimized so that they develop a positive lift at an appropriate range of angle of attack. Whereas if you look at the tail of that same airplane where it has a rudder, where you want it to be just as good at turning left as it is at good turning right, then you want to use a symmetric body so that its performance is the same in either direction. But here we go. So the idea of how these work, right? How wings work, you've probably heard, whether it was in elementary school, like Bill Nye style science programs or whatnot, or some of you have kind of poked around in aerodynamics. Anyone having that kind of the theory of how wings generate lift that they think they know? Pressure difference. That's exactly right. Let's try this actually. The theory that I always was told when I was growing up and an undergraduate was that two particles, right, are traveling together and they split up, right, and the one traveling over the top has further to travel in the same time than the one on the bottom, and so it speeds up. And then Bernoulli takes over and says there's a pressure difference. Is that something that people have heard before? Okay, that's completely wrong. That's called the equal transit theorem, and it has been debunked time and time again, but they still teach it in flight schools and engineering classes, but it's not actually correct. So the idea there is that relies on the idea that two fluid particles have to meet up with one another after they are done traversing the wing, which isn't really true. This is a much more accurate way of looking at it, where this particle speeds up, but it's not because it has further to go, right? In fact, at the end here, it's nowhere near the particle it started out next to. So that there is just saying, like, the flow over the top moves faster. That's correct, but it's not because it has further to go. In reality, it has more to do with the curvature that you're introducing into the flow. Remember we talked about how the Bernoulli equation applied across streamlines says that if a streamline curves toward an object, that indicates, or if it curves in a direction, that indicates the pressure in the direction of curvature is lower. Okay, low pressures tend to go along with curvature toward those regions. What really happens, it's hard to really parse out the cause and effect here, but flow comes along, right? It's going to traverse over the top. If it wants to just go straight, what's going to happen is it's going to create a vacuum here, basically, right? Nature abhors a vacuum, right? So it's going to tend to be sucked back in. That curvature goes along with a reduced pressure along the top here. And along with that, right, that low pressure and that curvature also causes an acceleration of the flow, so it speeds up. And so it has more to do with the shape of the streamline than anything else and how that low pressure is developed. But what happens is that the flow over the top, because it speeds up, let's do this. Let's assume that out here, the pressure is something we call P naught. Okay, that's the ambient pressure. So the pressure over the, and this y-axis we're going to call P minus P naught. So the pressure over the top is going to be, it's going to reduce. It's going to be smaller than P naught. In fact, it's going to look something like this. Okay, so this is the flow over the top, and the flow over the bottom is going to actually increase in pressure. It's going to slow down. And so if you took this pressure difference, okay, if you integrated the area under each of these two curves over, the surface area of the hydrofoil or the airfoil, what you would get is the total lift, right? The total difference in force. The other interesting thing, right? So let's say this is the negative pressure on the upper surface. Right, creates a suction effect. And the positive pressure on the lower surface pushes upward. So the fun fact here is that the way this is drawn is actually even a little bit underrepresented. About 80% of the lift on a wing actually comes from the suction effect on the top of the wing. And only about 20% comes from the increase in pressure on the bottom. So wings generate or lift more through the fact that they're creating a vacuum above them that sucks them upward than by, by creating a high pressure below them. This is why stall is such a big deal, right? Wings that stall out. That means that the wing inclines so far that it no longer looks like a streamlined body, and the flow will detach. And you end up with this messy region here that doesn't work to generate lift. And because it affects the upper surface, that can rob you of about 80% of your lift. And that generally makes things fall out of the sky. All right, so now that we've kind of talked about how the broad mechanisms of how wings work, let's talk about the where we find lift coefficients and how we use lift coefficients. So actually, this is still back over here. So we talked about the drag coefficient earlier, all right? But the lift coefficient is really the same idea. Okay, the drag coefficient and lift coefficient were defined respectively as lift divided by 1/2 rho u squared times an area, and drag divided by 1/2 rho u squared times an area. So these are the two pi terms that we use to represent these lift and the drag forces on an object. The question is what do we use for the area in these two? Right? What that a term that's in the denominator is not always obvious. For the drag coefficient, we said it's usually listed in a table. Okay. For the lift coefficient, it's often a little bit different. So for drag, it's usually the frontal area. I said if you were to stand upstream and you were to look in the direction of flow and kind of draw the outline of the silhouette of the object, that's usually the area that's used, that projected area. For the lift coefficient, the area is usually the plan form. That means if you were to orient yourself perpendicular to the flow and look at the object, what's the silhouette that it creates in that case? Another way of thinking about it is, for drag coefficient, the area is the area projected in the direction of the drag. For lift coefficient, it's the area projected in the direction of the lift. Wings like to make things even more difficult by usually using this planform area for both lift and drag coefficients, but don't worry, that will be made obvious to you. The primary thing to take away from this is that if you're using lift and drag coefficients, you need to be conscious and careful about using the correct area, or checking that you are using the area as it's given to you. and whatever's reporting your lift and drag coefficients. So let's actually do an example. So this is one that I've used periodically, is similar problems to this have shown up on a couple of exams in the past, a couple of in-class activities. But this is a Cessna 172 Skyhawk. It's the most, I think it's the best-selling plane in all of history. And it weighs about, or has a mass of about 1,000 kilograms. Okay. That is the, yes, so a mass of about 1,000 kilograms. And we're going to assume that it is oriented. Okay, it's flying such that the wing has a lift coefficient of 0.3. So at what speed does the plane have to fly to maintain level flight? And we're given some information about it in the form of the dimensions of the wing. Okay, C is what we call chord. That's the sort of the length of the wing. And S is the span. So in this case, 10 meters. So because we're talking about a wing section here, or a wing, the area used for both the lift and the drag is going to be the same, and that's going to be C times S. That is the plan form area of the wing, which is at 1.5 meters by 10 meters, so we're dealing with a 15 square meter area. So once we figure out how fast the plane has to be flying, we're going to say that the wing and the fuselage together, okay, have a combined drag coefficient still based on the wing planform area of 0.05. And when we know that, can we find what the actual power is required to keep the plane aloft? So the order of operations is, we know we have to generate so much lift in order to stay flying. We use that to figure out how fast we're going. Use that speed and the drag coefficient to figure out what the drag is, and then use the speed and the drag to figure out the power of the engine. So we're going to start out this problem with a free body diagram. Oops. So we'll assume this is our plane, right? And we know that it's got the weight of the plane acting downward. It's going to have the lift of the wing. There we go. Lift of the wing acting upward, and I wanted a red pen. There we go. And the drag acting in the direction opposite its motion, and then finally, right, we could show that the propeller on there is producing a, we'll call this F propeller. So first we're doing equilibrium in the Y direction, right? Oops, come on, there you go. X and Y. So we know that sum of the forces in Y, if we don't want the thing to be climbing or falling, to maintain level flight, has to be 0, which means that the lift has to be equal to the weight, which must be equal to mg, which is 1,000 kilograms times 9.81 meters per second squared, 9.8 kilonewtons. We also know the lift is equal to 1/2 rho u squared times a times the lift coefficient. Okay, so we've been given everything here except the value of u, right? The lift coefficient, we're told, is a value of 0.3. We've got 15 square meters. We're dealing with air, so 1.23 kilograms per cubic meter. And so our job is, and we just found the lift, it has to balance the weight, so our job is to find the speed. So U is going to be equal to square root of lift divided by CL times 1/2 times rho times A. 9810 newtons divided by 0.3 times 1/2 times 1.23 kilograms per cubic meter times 15 square meters will work out to be 59.33 meters per second. For those that think in imperial units, that works out to about 133 miles per hour. So a pretty moderate cruise speed for a small aircraft. Okay. Second part of this, is the drag, right? So we know that the drag has got to be equal to drag coefficient times 1/2 rho u squared times A. So we're told the drag coefficient is 0.05. We're told that the area for the drag coefficient is, just like with the lift, is going to be based on the wing area. And now we have a velocity to work with. So we can actually calculate the drag force. So we're dealing with 15 square meters. We're dealing with our 59.33 meters per second and 0.05 for the drag coefficient. So plugging in those values, we should end up with 1,630 newtons. So we know the drag, we know the lift, we know the speed. Find power, right? The way to calculate power is the force times, the force being applied to a moving object times the speed at which that moving object is traversing, right? And so the power produced by the prop, well, to keep it moving at a constant speed, the idea is that the force of the prop has to counteract the force of the drag. And the power is going to be F prop times the speed of the aircraft. So that's going to be our 1630 newtons times 59.33 meters per second, right? Newton meters per second. That'll give us watts. It should work out to 97,300 watts. So 97.3 kilowatts, or about 130 horsepower, 130.5 horsepower. So, small car engine, which is about the size of the engine of these things. So, I should ask, are there any either amateur or licensed pilots in the room? Yeah, I've had a couple of pilots in the room that look at me like I'm an idiot the whole time I'm doing this exercise in the past. But okay, any questions? All right. Wings are one of my favorite topics. I can go on for days about them. I'll spare you. But what I do want to mention very quickly is the way you usually find like this lift and this drag coefficient for a wing. And that's going to be using tables or plots like this. So this is a very typical way of reporting the forces on a wing. And so usually what you'll do is you'll find a wing that has a specific type of geometry. You'll have a name. Like Clark Y is a type of wing profile. It's actually the one that we used to use in the lab for this class. And so the top there says Clark Y airfoil. Okay. On the x-axis, you'll have the angle of attack. That represents the inclination with respect to flow. And then you'll have the lift coefficient, okay, on the x-axis, and the drag coefficient on the y-axis. So for most wings, the lift coefficient is going to increase pretty linearly with the angle of attack, and the drag is going to vary quadratically with the lift. So since that varies linearly with the angle of attack, it'll vary quadratically with the angle of attack as well. So without getting real deep into the theory, the idea is find the angle of attack, look up the lift and drag coefficient at that angle of attack, and you're good to go. Another way that this problem could have been framed, okay, is I could have said, here's the speed of the aircraft, here's the weight of the aircraft. Find the lift coefficient and find the angle of attack. Okay? In that case, you would have found the lift coefficient by saying, oh, our total weight of the aircraft is about 1/2 rho u squared times area. You would have said, maybe that lift coefficient is 0.5. Bam. What's the angle of attack, that lift coefficient? Right around 2 degrees. What's the drag coefficient at that point? Maybe about 0.03. And you would have had the same, been able to work out the same solution that we just did. What happens up here at the top, I mentioned, is this effect called stall. And what that looks like is, here's this video of this airfoil that is being inclined and inclined. You can see the flow is attached, the flow is attached, the flow is attached, and then the flow detaches, right? This is what's called trailing edge stall. And what happens there is that the lift begins to jump off a cliff, right? As you increase the angle of attack further, your lift just decreases. So that's why the conventional wisdom is, for pilots, if your wing stalls out, you're supposed to go into a dive, right? You're supposed to try to decrease your angle of attack down into the region where the flow is reattached and you regain control. All right. Last little thing to mention here is what's called the Magnus effect. Now, I mentioned this very briefly when we were discussing ideal flow or potential flow in that kind of survey lecture. The idea here is another way of introducing asymmetry to the flow, right, to produce lift, is instead of changing the shape of the object, you can rotate that object, right? And what will happen is that, for example, for a sphere or a cylinder, the flow will tend to, if you're rotating it like this, the flow will tend to get pulled along with it. And so the flow will look like this. This introduces asymmetry, and because of the direction of rotation, the flow over the top is going to be moving faster than the flow over the bottom. Lower pressure on top generates lift. This is the logic behind a fastball, okay? Or really any kind of ball that uses spin in order to change its flight trajectory. And we actually have expressions here for how rotation of a smooth sphere affects the lift and the drag. So I don't have time to work all the way through the example that I have written out here, but I can do, again, kind of the broad strokes. So let's say we have a ping pong ball with a given mass. Okay, say it's given a good whack and leaves the paddle at 12 meters per second with a backspin of 6,000 RPM. So someone really puts a ton of backspin on it. The question is, what is the acceleration vector of the ball? Okay, vertical and horizontal acceleration at the instant that it leaves the paddle. So we would say, right, this works out to 100 rotations per second. Oh man, that's ugly. And which means you have to find omega is going to be, right, 2 pi times 100 radians per second. And to find the acceleration, the idea is a free body diagram is going to come into play, where you find the lift, you find the drag, and then you know the mass of the ball. So when it's traveling at 12 meters per second, you have your velocity, you know the area because you know the diameter of the ball, and then the backspin you can use to find the lift and the drag coefficient with this plot here. So it turns out that with the conditions given, our omega d over 2u works out to be about 0.995, so that means we're running right around here, and we get a drag coefficient of about 0.5 and a lift coefficient of about 0.25. One and a half rho u squared times 0.25 times pi over 4d squared, right? Drag, same thing, but with 0.5, the drag coefficient, and you just do a sum of the moments is equal to mass times acceleration. Once you find the net forces, and you can find the acceleration vertically and horizontally. And the net result here is that it'll actually, the ping pong ball will rise at about 0.2 meters per second squared. Okay, that does it for the lecture material. So I'm going to go ahead and put the quiz up on screen here. And if you guys have any further questions on lift, I am happy to entertain those. And then on Wednesday and Friday this week, we're going to have some wrap up and in-class activities. So please show up for those. Okay, so Monday quiz, 12:06. There we go. And I will go ahead and pull up a copy of the Moody diagram. And for the fluid properties, if you need to look those up, look in the tabulated fluid properties page on the icon modules.